Good morning, dear students. Let's take up first module. The first topic what we have is Coulomb's law. This experimental Coulomb's law says, Coulomb states that the force between two very small objects separated in vacuum or free space by a distance which is large compared to the size is proportional to the charge on each end inversely proportional to the square of the distance between them. We can write it in an equation form. F is equal to K into Q1 into Q2 divided by R square, where K we call it as proportionality constant here, that can be defined as K is equal to 1 divided by 4 pi epsilon naught. The Q1 and Q2 are the charges and R is what the distance between the two charges. So according to the Coulomb's law, it states that the force is equal to K into the two charges we have in the numerator, that is proportional to the charges, and it's inversely proportional to the square of the distance between them. Here remember one condition, that is the charge should be less than the distance between the two charges, that is Q1, Q2 values or whatever we are talking about should be less than the distance here. What will happen if this distance is small and the charges are bigger? You may find that the distance, if you find it smaller, the charge Q1 and Q2 may overlap. So because of that, here we have a condition that is, the distance should be large enough compared to the size of a charge on the 2 points we have 1 and 2 here. The SI units of the quantities what we have in the Coulomb's law. We say that the Q are measured in coulombs and the separation R is in meter. This is what the standard SI unit of meters, and the force should be Newton. I repeat, in SI unit, if we represent here the Coulomb's law, then we have quantities Q1, Q2 are measured in coulombs, and the separation, which is a distance which is measured in meter, and the force should be Newton here, which we have a capital N represented here. This will be achieved if the constant of proportionality K is written as 1 divided by 4 pi epsilon naught. We know that epsilon naught is the permittivity of the free space, is measured in farads per meter, and has the magnitude of, that is two way we can represent. One, we have 8.854 into 10 power minus 12 farad per meter, and another form of epsilon naught we can represent it as 1 divided by 36 pi into 10 power minus 9 farad per meter. We will be using both the values, both the values in a few problems. Wherever we have a pi in the equation, before we substitute epsilon value, if we have a pi in that equation, we prefer to use this equation. Otherwise, we will be using this constant value what we have here without pi. So one, we have epsilon with, in terms of pi, another value we have equivalent value without pi. So we will just see the situation, based on that we will be using these constants. So now the Coulomb's law, we can write it as F is equal to 1 divided by 4 pi epsilon naught into Q1, Q2 divided by R square. So this is what the force equation we have according to Coulomb's. And we know that, the force F acts along the line joining the two charges. It is repulsive if the charges are alike in the sign and attractive if are of opposite sign. What does it mean? If the charges Q1 and Q2, if they are of same type, that is positive, then you could see that the force will be moving in this way. That is, force will go away here like this, what we call it as repulsive force. Now, both, we cannot have it. Whichever is bigger, we will be moving in that direction. Similarly, if the charges are in opposite, that is, one is positive, another one is negative, then you will see that a force of attraction exists here. And, now effective force is again based on which one is bigger. Say, for example, if this is bigger, you will see that this attracts this. And if this is bigger, we will say that this attract this, and you will be having a resultant force flowing from Q1 to Q2, else the other way it is Q2 to Q1. So this is about the force and its definition according to Coulomb's law. We have now a situation where Q1 and Q2 are situated like this, and they are having a distance R1 and R2 respectively from the origin, what we have here shown in the figure. Now, if I join Q1 and Q2, I'll be getting a vector R12, and its modulus is what the length we could see here. Similarly, here is what the vector R1, that means from origin to Q1, if you are joining, you will get a vector. It is R1. Again, modulus of that is what the length we have here. Similarly, R2, we can define it as the length from origin to the charge Q2 where it is situated, and this is what we call it as vector R2, and modulus of this is what the length we have here for R2. Now, we can now relate these three vectors now, where R12 is what the vector here, that is the length or the line we got it by joining Q1 and Q2. This R2, R2, R1, I can just relate now. And this is what we call it as triangular rule, which we have already discussed. What is triangular rule here? Triangular rule says that if vectors are connected in a triangular form, something like this, then if you apply a triangular rule here, you can see that you can write an equation based on its direction. Algebraic sum of these vector which are arranged in the triangle will be 0. Now let us trace the vector now. Here I have vector R1 in the direction like this. In the direction of traversal, whatever I am doing, I have R1 in the same direction. So this becomes positive R1. This is again, R12 is again in the direction of traversal. So R12 vector is also positive. Looking to the vector R2, this is in the reverse direction of traversal. So this becomes negative now. So algebraic sum equation, if I write, it is R1 plus R12 minus R2 is equal to 0. So from this triangular law, I can write an equation for R12, which is equal to, I can say that R1 minus R12 is equal to R1 minus R2. Else I can say that R2 minus R1 is equal to R12. I can write that equation according to the triangular of, in a triangular law, we call it as. So now we define a unit vector. What is a unit vector? Unit vector we can have along any vector direction, which is having a length which is equal to 1 in the direction of the vector itself. So R12 is a vector I have. I can just represent a unit vector in that direction, which is having a length or magnitude 1. So we have a standard formula for calculating a unit vector. So I can say here we have written that unit vector in the direction of R12, I call it as A12, which is equal to the vector divided by its modulus. Because from the vector, whatever magnitude it is having, I should divide that vector by that magnitude so that I left out with the unity. That's what we want. So I'm going to have a constructive vector here, which is having a assured magnitude of 1. So for any vector for that matter, we can just have a unit vector construction possible. Only thing is we have to divide a vector by its magnitude to get a unit vector. So this is what the formula we will be using to calculate a unit vector in any vector direction. So why we should learn this unit vector? Because the Coulomb's law, which we have stated, if you wanted to express the force direction, then you require a unit vector. If you multiply that force definition by a unit vector, then the force will be now become a scalar representation, we call it as. So this is what we have, a scalar representation of a Coulomb's law. That states that the same expression what we have, that is what we call it as Coulomb's law in scalar form. Now we are converting that to vector form by just multiplying by a unit vector. So unit vector in that direction we have taken here, and the force equation what we got it in the previous slide, we are multiplying by that to get a Coulomb's law defined here in vector form. So this is called vector form of Coulomb's law. What we did is just we have attached a unit vector here so that the force equation now becomes a vector form. F2 is the force on Q2 for the case where Q1 and Q2 have the same sign, while A12 is a unit vector in the direction of R12, the line segment of Q1 and Q2. So you could see here, I could have a force F2 moving in this direction. What does it mean? Q1 and Q2 are of the same polarity. That's why we are finding the repulsive force. So you will get a force going away. So it depends on whichever is bigger, you will be moving in that direction. So I'm having a F2 here. That means the repulsion force of Q2 is bigger than Q1 is bigger than Q2. Otherwise, you will be moving this way. F2 would have been in this direction if Q2 is bigger than Q1. So this is about the Coulomb's law representation in vector form and the resultant F direction. Here we have a small example of calculation of force. So here we have a charge Q1 with a value given and Q2 charge is also given, and they say that they are located in vacuum. So we have to determine the force experienced by Q2 by Q1. Remember, it is Q2 by Q1. So how much is force that Q2 is experiencing due to Q1 is what we have to calculate. So R12 is what we have to calculate. This we have seen in the previous class, previous slide, how to construct a R2 vector and how to construct an R1 vector. So they have given here the location of Q1, that is X coordinate, Y coordinate and Z coordinate is 1, 2, 3 given. And for a charge Q2, where it is located, it is given by its Cartesian, what we call it as location, Cartesian form of representing a location here we have, that is 205. That means X coordinate is 2, Y is 0, Z is 5. So they have given here location of Q1, they have given here location of Q2. You can construct vector R1 and vector R2. This is how we have constructed the vector R2. Vector R2 is the distance of Q2 from the origin that we have here minus the distance of Q1 from the origin that we have here. So R2 minus R1, we have done it. We got a value vector R12 here. Now unit vector, how to compute? It is R12 divided by its modulus. So R12 vector we have just computed by computing R2 minus R1. And here R12 divided by modulus of R12, we have done it to get a unit vector in that direction. Now this is what the F2 we have according to the Coulomb's law in the vector form. This is what we have. Just the substitution we have done it here. Remember, we have done epsilon naught substitution here, not as the function of pi here. This is a constant 8.854 into 10 power minus 12. We have substituted for epsilon naught. For pi we have just taken as it is. And you can just have it this pi form also, so that pi and get cancels with the pi what we get by epsilon naught representation. You can even do that. Q1 and Q2 we have substituted here, and A12 we have taken here. So after simplification, you will be getting a equation for F2 something like this: minus 10 AX plus 20 AY minus 20 AZ. So much of Newton here. So this is what the force F2 in Cartesian form representation which has been done, and this is a vector form. So this is a vector we have force F2. So we know that F1 is equal to minus of F2. So if you multiply this vector F2 by minus, you will be getting what we have, force F1. What is F1? That is force exerted on Q1 by Q2. Thank you.